Welcome back, focused learners, to our latest explainer. We're diving into Series 3, Episode 13 of our journey through the foundations of general emergence mechanics. Now, in our last session, we talked about emergent constants, right? We asked if massive cosmic quantities like the speed of light are actually just stable readouts of a deeper geometry. Well, today, we're totally shifting our scale. We are zooming way, way in, moving away from the cosmos and dropping directly into the mechanics of molecular chemistry. We're going to see how GEM isn't just this abstract language for gravity and light. It's actually a profound framework for understanding molecular form and biological selectivity. Let's get into it. Here's a quick look at our roadmap today. 1. Chemical handedness. 2. The persistence question. 3. Z3 and Z2 landscapes. 4. Bias without forcing. 5. Persistence asymmetry. And 6. Biological amplification. All right, starting right off with Section 1, chemical handedness. So in chemistry, we have this concept called chirality, or chemical handedness. This basically refers to molecules that naturally exist in distinct left-handed and right-handed forms. The easiest way to visualize this is to just think about your actual hands. They are made of the exact same parts, right? 4 fingers, 1 thumb, a palm. And they are perfect mirror images of each other. But try as you might, there is absolutely no way you can perfectly superimpose your left hand over your right hand in 3-dimensional space. They just don't line up.
And honestly, this brilliantly illustrates why this concept is such a huge deal in biology. You've got a left-handed form and a right-handed form. Now, traditional stereochemistry tells us that these two mirror forms contain the exact same atoms and the exact same bonds, same exact ingredients, yet they interact very differently with biological systems. It's wild. One form might fit perfectly into an enzyme or a protein receptor, while its exact mirror counterpart utterly fails to fit, or, maybe even causes a completely different, sometimes dangerous reaction.
Moving right along to Section 2, the persistence question. Okay, so traditional chemistry usually relies on molecular geometry and orbital structure to explain this handedness. But GEM steps back and asks a much deeper question. Why does handedness actually persist? What makes a mirror branch not just mathematically possible on paper, but dynamically admissible in reality? Because in GEM, there's a core rule. Possibility is not persistence. Think about it. A structure can absolutely be chemically possible, but if it is just way too energetically costly to maintain when the environment pushes back against it, it simply won't hold together. A structure only sticks around if it stays admissible inside what we call the coherence shell. Which brings us to Section 3, Z3 and Z2 landscapes. Let's look at the math. The big GEM breakthrough here is that chemical handedness can actually be understood as a Z2 twist on top of a Z3 phase landscape. I know that sounds like a mouthful, so let's break down the Z3 structure first. It's defined as V sub 3 of theta equals minus mu times the cosine of 3 theta. This seemingly simple equation is super important because it creates a threefold phase landscape. Basically, it divides our phase space into 3 repeating, low-cost sectors. The preferred stable phase directions sit at 0, 120, and 240 degrees. This threefold setup gives the system its foundational geometry for admissible phase organization. Now, on top of that, we add the Z2 operation. Z2 is our mirror or parity operation. It literally represents a binary split, left versus right. Just look at the equations. We've got theta L for the left-handed branch and theta R for the right-handed branch. Notice how they both branch off from a central reference phase, which we call theta 0, and they're displaced by a parity-sensitive shift represented by delta. So when you combine them, a Z2 twist over that Z3 landscape is exactly what creates our distinct left-handed and right-handed branches. Okay, Section 4, bias without forcing. This is where it gets really interesting. So, when we combine these mathematical structures, yes, the two branches are mirror-related. But once you factor in the messy reality of the environment, they don't necessarily carry the same persistence cost. This introduces our chiral bias term. V bias of theta equals minus kappa times the quantity cosine theta plus the square root of 3 times sine theta. Now, zero in on that root 3 term. That is a geometric signature. It's a direct mathematical fingerprint of that 60-degree sector structure we get from our threefold landscape. Putting it all together gives us the effective landscape, VF. The first half gives us that repeating Z3 sector pattern, and the second half adds the chiral tilt. Now, this is absolutely crucial, so keep this in mind. This twist does not force one branch into existence. It simply tilts the landscape.
We call this bias without forcing. Both branches are still 100% mathematically possible, but the terrain itself is tilted. The system isn't being commanded to pick one outcome, it's just being nudged.
Which leads us to Section 5, persistence asymmetry. So what's the actual cost to maintain these structures? We measure the admissibility cost of the left branch against the right branch, and we call that difference delta ALR. Now, if delta ALR equals exactly 0, the branches are what we call persistence degenerate. It's a tie, there's no bias. But if delta ALR does not equal 0, then we have a handed persistence bias. And remember, this absolutely does not mean the losing branch is impossible. It simply means one branch pays a lower phase stiffness cost. It is literally cheaper to hold together. Nature is incredibly frugal, you know? A bias just means one path requires less energy to maintain.
Finally, Section 6, biological amplification. Let's look at how this plays out in life.
Let's rethink a really classic biology concept. The traditional view uses this lock and key model, basically saying the wrong-handed molecule simply doesn't fit the biological lock. It's a mechanical matching problem. But the GEM view goes much deeper. In GEM, a molecule is actually a curvature pattern, and a receptor is a permitted phase route. So the wrong-handed molecule isn't just a physical key that doesn't fit, it's a curvature pattern that fundamentally cannot route through the available coherence channel without paying a massive, excessive phase cost. And we have to remember, GM isn't trying to replace stereochemistry or quantum chemistry. It sits right underneath them, providing the foundation. In total isolation, the left and right forms might be practically equal. But inside a dynamic, chiral biological environment, life itself acts as a massive amplifier. Enzymes act as these highly specific coherence channels. So these tiny, tiny differences in how efficiently phase curvature is routed become hugely significant over time. Because one branch is even slightly cheaper to hold, that environmental filtering and biological amplification eventually turn that tiny little structural tilt into a decisive, hard and fast rule for life. So, what is the ultimate takeaway here? Handedness is not imposed, it is filtered. The coherent shell doesn't have to outright forbid a mirror structure to make it super rare in biology. It just has to crank up the cost of its persistence. The landscape doesn't command, it simply tilts. Chemical handedness really is one of the clearest, most elegant early tests of general emergence mechanics, beautifully bridging pure abstract phase geometry with the real-world complex chemistry of life. So I want to leave you with this final thought to chew on as you review these concepts. Does nature intentionally choose handedness, or does it simply quietly filter out what cannot hold? Something to think about. Keep exploring, focused learners, and I'll catch you in the next explainer.